We're going to work a couple more examples on these improper integrals because I just want you to see how easy, really, that the process is. But when the limits are involved, you've got to think about nearness and tiny and huge and all that. So I wanted to do some more examples. Here's an example of a multiple choice question. Which of the following gives the value of the integral from 0 to 1, 1 over x minus 1? Clearly here this is an improper integral where our upper limit is the one that's giving us trouble. So we're going to introduce the limit as b approaches 1 from the left. We want to be inside the integral. 1 over x minus 1 dx. This is a u substitution. This part we can do really easily. So our indefinite integral would be 1 over u du. Antiderivative, natural log of u plus c. So back to our limit, we have the natural log of x minus 1 from 0 up to b. Fundamental theorem, as b approaches 1 from the left, the natural log of b minus 1 minus the natural log of 0 minus 1. This one is definitely where we need to bring the absolute, that goes there, the absolute value to our antiderivative function because we're going to have a negative input value there. All right, so let's see what's happening here. As b gets really, 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 really close to 1 from the left, then something almost with a value of 1, taking 1 out of it, will leave us negative tiny. So in the absolute value, right, there's absolute value, we get to call that positive tiny. So for positive tiny input values on the natural log function, here's the natural log function, and there's 0, so positive tiny input values are just to the right. What are the outputs doing? Well, the outputs are headed to negative infinity. And here, the natural log of 1 is 0. So this is diverging. So the function doesn't get close enough to that vertical asymptote at x equal 1 to have the area go ahead and stop growing. So hopefully with these examples, you'll kind of get an idea of what's happening here. Here we are integrating from 0 to 2, but we have a function that is undefined for a value of 1. So we're going to have to split this integral up because we're going to have to approach that vertical asymptote that's running right down the middle of our interval. We're going to have to approach it from 2 different sides. So we introduce the limit as b approaches 1 from the left, from inside the interval, right, 1/3 dx, plus the limit as a approaches 1 from the right, again, inside, x minus 1, 1/3 dx. This is a u substitution. U equals x minus 1. du equals dx. We have u to the negative 1/3 du. The antiderivative is 3/2 u to the 2/3 plus c. If it was multiple choice, you wouldn't really have to do all of this work, but I suggest right up front that you do. I suggest that you show your limits and all that kind of stuff and really try to make sure you're doing every step along the way correctly. So 3/2 x minus 1 to the 2/3, and we are integrating from 0 to b, plus the limit as a approaches 1 from the right, 3/2 x minus 1 to the 2/3, and we're integrating from a up to 2. So the limit as b approaches 1 from the left of 3/2, upper limit is b, lower limit is 0. There's fundamental theorem for your first integral, plus the limit as a approaches 1 from the right. The upper limit is 2, and the lower limit is a. So there's fundamental theorem. So here's the part we need to pay attention to. Here, again, we're very, very, very close to the left side of 1. So what's left is negative tiny. That's going to 0. This is a well-defined value. It's negative 3/2. Oh no, that's squared. So that's just a negative 3/2. And then here we have plus 3/2 times 1. That's 3/2. And here we're plugging in 1.000, whole bunch of zeros, and then 0, 1. So something a little bit bigger than what's here. That leaves us positive tiny. That's going to 0. So this does converge, and it converges to that value. So there's just a second quick example. I have one final example that I want to go through, and this is a piecewise defined function. Usually the more complicated that our calculus gets, the more thought that it takes. They don't really throw us curveballs and have us think about things, but sometimes they do. I kind of sort of, this is a little theoretical. They want to know, are you thinking about more than just, do I have a vertical asymptote and how do I do that? Are you thinking about everything that's going on here? So here, they've asked you to determine if the area accumulating in the plane under F, or between F and the horizontal axis, over the interval from 0 to 2 converges or diverges, and then they give you F as a piecewise defined function. So you've got to look at the two pieces of F. Here's one and here's another. There are two pieces of F. For one piece, F acts like this. For another piece, F acts like this. And so for all values less than or equal to 1, we have this. And for all values between 1 and 2, we look like this. Now there's a little curveball here. Yes, we have issues from 0 to 1 at 0 on that first chunk. So when we're integrating from 0 to 1, this function's not defined at 0. So we need to introduce the limit just on this first part. As a approaches 0 from the inside the interval, right? And we're going to integrate from a to 1. And we could go back and write this as x to the negative 1/2. That would be easier to find the antiderivative. So that's that part. Not a problem. Because we equal 1. This says I can plug 1 in and use 1. So I have a well-defined upper limit here. Not a problem. However, I don't here. Be very careful. This part looks like it's really innocent. And you say, well, yeah, that's well-defined from 1 to 2. That's not a problem. There's no vertical asymptote there. Let's just integrate from 1 to 2x dx. Well, that will be a distractor. It'd be the number 1 distractor. Because this tells you you can't plug in 1 and you can't plug in 2. You're going to have to break this up over some interior point, and it doesn't matter what interior point. And then you're going to have to introduce the limit to approach 1 from the right and 2 from the left. So let's do that. And I'll get a different color to do that. Let me clean this up. And we'll have to remember to go back and include this with it, because this is in addition to this. We have this other interval that we're going to look at. So we're going to integrate the limit as a approaches 1 from the right, from a up to, and I mean any interior point here, it doesn't matter. we'll just pick the middle point, x dx. And then we're going to have to add to that the limit as b approaches 2 from the left from 3/2 up to b, x dx. So that's what this entire integral is going to look like as a approaches 0 from the right, from a up to 1, x to the negative 1/2 dx, plus the limit as a approaches 1 from the right. Give myself some room here. From a up to 3/2 x dx, plus the limit as b approaches 2 from the left, from 3/2 to b, x dx. And so that's not really obvious. This is kind of a little bit of a curveball here. So let's find our antiderivative functions. And here the antiderivative using the power rule is 2x to the 1/2 that we're going to evaluate from a up to 1. Here, please don't drop your limit notation. The antiderivative is 1/2 x squared, and we're evaluating from a up to 3/2. And then I'll drop down here. The limit as b approaches 2 from the left, 1/2 x squared from 3/2 up to b. So we have the limit as a approaches 0 from the right of 2 times 1 to the 1/2 minus 2 times a to the 1/2 plus the limit as a approaches 1 from the right of 1/2 times 3/2 squared minus 1/2 times a squared. And then lastly, plus the limit as b approaches 2 from the left of 1/2 b squared minus 1/2 3/2 squared. So get another color and we'll plug these values in. Here we clearly have 2, the square root of 1 is 1, minus 0. As we get really, really, really close to 0, the square root of 0 is 0. And then plus, next we have a well-defined value, 1/2 times 9/4 minus. 1 squared is 1. I'm plugging 1 in there, and inside the limit, I can do that. Remember, the first thing we do to evaluate a limit is plug the value in. So when a equals 1, 1 squared is 1. 1 minus negative 1/2 is negative 1/2. And then plus, as b approaches 2, I get to plug 2 in. That's 2 squared, that's 4. 1/2 of 4 is 2. And then a well-defined value, 1/2 times 9/4. So this one clearly converges. And so if one of the choices up here is non-existent or diverges, yeah, so that one's out. This one clearly converges. So here I have a 2 and a 2, that's 4. If I'm going to make a mistake, here's where I'm going to make it. Those two cancel. And so it looks like it's 4 minus 1/2. So hopefully one of those choices is 7/2. And it is. So there we are right there. I wanted you to kind of see that little curveball there. You've got to think about whether your limits of integration are included. And if they're not, then you have got to introduce the limit because you can only get near those values, not at those values when you're doing fundamental theorem. So there we are. There's a second lesson for improper integrals. Come to class next time. We'll work some more homework problems.